Hello and welcome to another video presentation provided by the University of North Texas Physics Department with the assistance of the Physics Demo Room. My name is Corey Nook and I'm going to be helping with a video presentation along with an actual physical demonstration of something that we like to call simultaneous fall. This really is looking at a physics concept of two-dimensional motion. So how this is really going to work is that we have two objects. You might have seen this demonstration done before on Mythbusters, only with they're using bullets, we're going to just be using wooden balls. Is that I'm going to have one object here and one object here. This object is going to be released and allowed to drop, and this object is going to be fired at a horizontal velocity. No vertical component to it at all. And what we're going to witness and also verify using physics is that even though this is shot off with some vertical, or should I say horizontal velocity, the amount of distance and the amount of time for these two to hit the ground is the exact same. This only works because we are shooting the other one perfectly in the x direction. So now, if we are going to set up this problem to confirm that yes, the time for each object should be the same, we have to be a little bit careful because this can get really messy in a really big hurry. So one of the things I like to do with these kind of problems is break it up into each object. So for example, I broke up over here, I drew my picture to where you can see that I have a dot representing mass 1 and another dot representing mass 2 that's fired in the horizontal direction. So with mass 1, I kind of gave it a Roman numeral 1 to establish this is for object 1, and Roman numeral 2 to establish this is for object 2. The reason why I did this is because later on you're going to be working with some similar kinematic equations, and I don't want to get them confused of what variables are supposed to go where. So if we look at just with situation 1 and ignore ball number 2 completely, we just say it's ignored, don't look at it, it doesn't exist, there is no ball 2 in Bossing saying. We see that we have the ball at some initial velocity in the y direction of being 0 meters per second. But we do realize that the ball is h meters above the ground. I'm saying h instead of a generic number because h allows us to have it for any situation instead of one specific one. Now I know that some of you might not exactly appreciate us using a constant that is not a number, but we're doing this for a generic result that you can hopefully apply to several different situations instead of just using a number and not really knowing how to work a problem. So with situation 1, I'm only looking in the y direction, but I want to relate this in terms of time. So instead of going and writing down all 4 kinematic equations, or 4 depending on how you view things, instead of writing all 4 kinematic equations, I believe that the one that we'll need with this problem has to deal with our y final position, or y sub f1 is equal to y initial sub 1 plus v initial 1 times time plus 1/2 times the acceleration in the y direction times time squared. Now with this case, remember that the acceleration in the y direction is going to be negative g, because we are at a value of positive h above ground, whereas ground, which will be our final y position, is a big goose egg, 0 meters. And the initial position is going to be h. This initial velocity in the y will be 0, but then this 1/2 a sub yt squared will be the only term besides this initial position to be non-zero. Okay, so this means I have 0 equals h plus 0 plus 1/2 the negative gt squared. So I can solve time in relation to position. But this is one equation and 2 unknowns. So I have to look at another object to kind of go, well, actually this isn't one equation, 2 unknowns. This is one equation, 1 unknown, because I know what the height is, presumably. I can say what the height actually is, it's a constant. I know that. So the only thing that I don't know is time. Oh. So now I can say, well, if this is the time here, let me see what the time is for object 2 and ignore object 1. So if I'm only looking at object 2, I'm at some height above the ground, h. I have some initial velocity in the x only, but not in the y. So now with this, that I know that I'm going to be traveling in 2 dimensions, what I'll usually do is I'll break up each dimension in terms of its x variables and its y variables. And I'll try to create a little table to separate them. Because in both the x and y direction, they use the exact same formulas, but they'll have different meanings for our kinematic equations. Because one's going to be only in the y direction, and the other set's going to be only in the x direction. The only thing that's going to interlay between those two is time. Now, you might be thinking, why is time the connecting variable between the 2 dimensions? Well, that's because if we go back to our definition of time, time is just looking at how events elapse over some experience and over events. So now let's say if I was to move in 2 dimensions to where, let's say, I'm going to go to my left and I'm going to just bounce up and down. That's moving in 2 directions. Or even if I was just to simulate with my hat 2-dimensional motion, that if I go left and I go down, I'm moving in 2 dimensions. But at the same time, you probably saw on your video screen that the time was still going. So even if I only looked at the x direction or the y direction, they have to connect with time. Doesn't matter. So now if I look at my x variables and I look at my initial conditions, the initial position in x is 0 meters. My final position in x, I don't know. Didn't put that up here, that was my fault. My initial velocity in the x is just going to be equal to v initial. My final velocity in the x is going to be equal to my initial velocity because my acceleration in the x is 0 meters per second squared. Once it gets pushed, there's nothing acting on it anymore in the x direction because we are ignoring air resistance. Then finally, we have time, which is our unknown variable. Now looking at the y direction, our initial height is h. Our final height is 0 meters, I should be more careful. Our initial velocity in the y is 0 meters per second. Our final velocity in the y we don't know because our acceleration is present as negative g, or negative 9.8 meters per second squared. And our final time is unknown. So now we've got to think about, now that I have all my initial conditions, I know what I can work with my kinematic equations, I'm going to look at something very similar to what I did for object 1. But I'm going to use that equation for both the x and y direction. So you'll see here I have y final sub 2 is equal to y initial 2 plus v initial in the y direction 2 times time plus 1/2 of a sub y t squared. Now you notice with the a sub y, I didn't put a 2 with that. I just left it as just a sub y. That's because I knew with both objects, it's going to be accelerating at the same rate. But now in the x direction, I have x final sub 2 equals x initial sub 2 plus v initial x sub 2 times time plus 1/2 a sub x t squared. Well, if I was to ignore the y direction and only look at the x and compare it to object 1, this could get a little interesting. Because I don't know what is the final position. But I do know what the initial position is. I know what the initial velocity is, so I can get a time. Oh, okay. Same thing here. I know what the final position is for the height. It's 0. The initial height is h. The initial velocity is 0. And the acceleration is negative g. Wait a minute. This equation looks exactly like this equation for object 1, that they have the same initial conditions. So even though this second object has a component in the x, they have the exact same kinematic equations with the exact same initial conditions. So I should get the exact same time. That gives us a little bit of something to work with. Now, with this equation, with our x position, we don't know what the final position is. And we don't know the amount of time, but we do know the initial velocity. So that's one equation and two unknowns that we can't solve. So that's why we look at the y direction first. We'll solve for time, and we can plug into the x to see how far the second object will be shot across. But the biggest point with this experiment, with this demonstration, is that both object 2 and object 1, when launched from the same height, even though this is going to be moving in 2 dimensions, they're going to fall in the y dimension the same amount of time and hit the ground at the same time. So now for enough talking about the kinematic equations and how things are going to go, let's actually see it. Because it's all fine and dandy to actually look at things just using math. But some of you are kind of visual learners, sometimes like myself, and we're going to actually shoot this. So all this is that I have two wooden balls that are sitting right here. When I release this lever, this ball will drop. This ball will be shot out. I know it's kind of exact opposite of kind of how I shown it on the board, but it's the exact same principles. Only now I just mirrored it. So now, if we are very careful, I'm going to release this pin and we should hear two bounces on the table at the same time. I don't know about you, but that sounded pretty close to being at the exact same time from my end. So how about this? I'll reload this again. Make sure that it's nice and level. So again, why do I need to worry about this object being nice and level when I'm about to shoot it? For those of you thinking at home. Remember how we established this equation, is that the initial velocity has to be purely in the x direction. If I didn't have this at the x direction, there'd be initially level, there'd be two things wrong with this. One, this object would now be fired in an angle upwards, and the amount of time that's going to take for it to reach the ground won't be the same as the one that's just falling straight down. The other issue is that because this is one solid piece, if I was to rotate this, the initial height positions for both these objects would actually be different as well. So we no longer would have the same height initial condition, and our equations would be thrown off too. This is something to think about when you're actually performing your labs, is to go, what are some little details from the physics you understand to go, what do I need to be careful about when I'm doing these experiments? So let's do this again, and let's shoot the balls. Well, I'll find that ball later. Well, thank you for attending and watching this video with us, and have a wonderful day.